Good afternoon and welcome to everybody. I've been asked to, in this wonderful series that has been going on India's space exploration, I've been asked to talk about the future directions of space-based astronomy, astrophysics. I'm an astronomer and I use space-based facilities for my astrophysical research. And what I want to tell you today is about why we have to go to space to do astronomy and what is happening in Indian space research that is helping astronomy, not just for Indian astronomers, but for everybody in the world and where we are going. So that's the idea. And I first wanted to say that all I'm going to say is my own opinion. This is not representing ISRO's activities officially. This is my speech as an astronomer. So a lot of you will know that when we do astronomy and astrophysics, we differ from other scientific practitioners who work in the lab because we cannot go and touch our subjects. We cannot go to them. We cannot even change the experiment being the universe, which is just one. And as a result, we have to rely on what comes to us from very, very far away objects and the kinds of radiation they give out. We call it light, but light in a very general sense, um, light which are essentially electromagnetic waves. And this is the only information we have from celestial objects. Actually, nowadays, we also have gravitational wave information, but that is a very minor part of the information we have. So we have to be like detectives. We have very little information that comes from a star or a galaxy or a black hole or a neutron star. And we have to, from the information that comes to us, we have to be clever to first detect them and then analyze them to figure out what we are observing. And fortunately, actually, we have a very different kinds of information. It's just not one kind of light that comes to us. For thousands of years, people looked at the sky with their eyes, and of course, the eyes see one very specialized kind of radiation. That is what we call light, that our eyes are sensitive to. But if you can see that the electromagnetic spectrum has a whole range of kinds of radiation. In the middle, you can see this is on a log scale. So actually, it spans a very large span of energy and wavelength and frequency. But right in the middle is what we call visible light, which goes from blue to red. And those are the colors we can see with our eyes. But if you look at longer wavelengths than the red that we can see, which is longer wavelength means shorter frequency, so shorter energy. We have infrared, then we have microwaves, and then you have radio waves, millimeter waves, that kind of thing. And then on the other side, which we again, all that infrared to microwave to radio waves, we cannot see. But we deal with them in our daily lives. Of course, our mobile phones work on radio waves, our microwave ovens work on microwaves, etc. Our heat that we produce in the kitchen essentially has a lot of infrared. On the other side, higher energies, then we can see we have ultraviolet, we have X-rays, we have gamma rays, and all of these come together to give us information about whatever we are observing. And so we have to put them together and then, like a detective, figure out what's going on in the universe. And that is our main challenge. So, for example, you can see that in the infrared, we cannot really see with our eyes. But if we have infrared detectors, we can see much more than our eyes could see in light. For example, here is somebody who's holding a plastic bag. You cannot see the hand, but with an infrared camera, you can actually sense the infrared radiation coming out of the human body. And of course, it can see through the bag. Similarly, if you look at a butterfly in the infrared, it looks very different from the butterfly in the optical, and it gives you some idea of what's on the butterfly. Even on our body, you can see the different parts have different temperatures, and so they give out different kinds of light. As you can see in this good example, the sun looks so different in different parts of the spectrum. So in the visual, which is what we see with our eyes, it looks very boring with some spots here and there, but otherwise it is very boring. It's nothing there. I mean, so however, this is the same view of the sun. If you see in the UV, you can see those three sunspots actually are emitting a lot of ultraviolet radiation, and the whole surface of the sun in the UV and X-rays look very, very dramatic. And that is because there's a lot of activity that's going on, which actually emit high energy photons, which is not in the range that our eyes can see, right? And so we have to work in the ultraviolet and the X-rays to actually find out what the sun looks like. Similarly, in the infrared and the radio, the sun looks very different. All that has information about the sun. And so if you have to understand the sun, we have to understand. Similarly, for galaxies, I mean, we're looking at this, one of our nearest galaxies, MED1 or Cene, which is our nearest elliptical galaxy. And you can see in different parts of the spectrum, they look very, very different. And each one of these pictures has a lot of information that we have to analyze and understand in order to understand the galaxy. And only just looking at a galaxy's picture doesn't give you all that information. And that is because the star's color, first of all, reveals its temperature. So you know that the sun is 5,800 degrees Kelvin, and so it has a peak in the yellow-green part of the spectrum. But if you have hotter stars, you see their peak will be in the ultraviolet, and if you have cooler stars, their peak will be in the infrared. And so it turns out most of the radiation from a young star, which is very hot, 20,000 degrees or so, will be in the ultraviolet. So if you want to see them, there is no way we can use our normal eyes to see them. Similarly, each part of the range of the electromagnetic spectrum actually gives us information about different kinds of things in the universe: gas, hot gas, cool stars, hot stars, dust, etc., etc., etc. The problem is that if you can see, the atmosphere is transparent for only a small part of this electromagnetic spectrum. So around the optical and a little bit of the near infrared, the radiation comes right through to us. And in the radio, the radiation comes right through to us. But all the stuff that I talked about, ultraviolet, X-rays, far infrared, millimeter wave, all that kind of stuff, they don't come through the atmosphere. They are stopped by the atmosphere. Atmosphere is opaque. And this is why we need to put the detectors and telescopes for this part of the spectrum in space. And this is why an astronomer like me has to go to space. I don't have to go to space, but I have to send detectors into space, or our country or the institutions we're affiliated to have to send instruments into space to study all that information that comes all across the electromagnetic spectrum. There's another thing, I mean, as the radiation comes through the atmosphere actually refracts the radiation as it comes to us. So it doesn't come in a straight line. It comes through a very zigzag path. And that is because every layer of the atmosphere has a different temperature, pressure, density, which affects the refractive index. And that is why when a star's image is formed in say a focus, which you see on the right, you will see that the star's image moves around. And this is why stars twinkle. And if you take an image which has a very long exposure, you will find that the image is blurred. This is called seeing. And so this is why we choose really remote places on the Earth to put up the large telescopes. But even then, we really can't see the stars and the details of extended objects at the highest resolution because of the blurring due to the atmosphere. So when we go to space, there is no atmosphere there, and as a result, we can see the highest resolution images also. So it is not just the part of the spectrum that we are looking at when we go to space. We can also, even in the optical, where we can have ground-based telescopes observe, the highest resolution we can get from space. And that's why the Hubble telescope, which is a relatively small telescope, has a lot more to give us than the biggest telescopes on Earth. So you can see, I mean, one of the major instruments that are up there is, for example, NASA's James Webb Space Telescope, which was launched a couple of years ago, has now given us a view of some of these amazing objects, which are the farthest objects known in the universe, from a time when the universe was about 1/20th or 1/15th of its current age. And that can be seen, those things can be seen, even though James Webb Space Telescope is much smaller than the largest telescopes on the Earth, and that is because they don't have this problem of blurring. And this is why we get these spectacular pictures of the nearby galaxies or even distant galaxies using a space telescope that is reasonably small. However, it has got no atmosphere to blur its images. So one of the things I wanted to tell you is that a lot of this idea of space astronomy came from India. And that is because in stars, the classification of stars according to spectrum was done by somebody called Meghnad Saha, whose ionization equation was one of the initial physics equations that showed us how to find out about stars by looking at their spectra. And when Meghnad Saha analyzed a lot of the stellar spectra, they were picked up by this amazing person called Cecilia Payne-Gaposchkin, who worked at Harvard in her PhD thesis. It was the first PhD thesis done in America by a woman. She adopted Meghnad Saha's theory of ionization equation and showed that you can actually find out a lot about stars by using this equation. And one of the things Meghnad Saha had said is that a lot of information in a star spectrum and star's image is in the ultraviolet, and he had figured out that our atmosphere actually stops, the ozone layer actually stops the ultraviolet. So he had floated this idea that we have to put a telescope above the ozone layer. This is an excerpt from an obituary written after Meghnad Saha's death by Harlow Shapley, who was at that time Harvard's director when Meghnad Saha worked. And he had said that when Meghnad Saha had visited Harvard in the 1930s, he had said, why don't you come and build a telescope that can go up above the ozone layer into space and help us observe these stars? And I think from that idea, a lot of people now agree that NASA and before that, American scientists tried to figure out how to get a telescope in space. And eventually we have done in India as well. So I just wanted to say that the idea of sending a telescope into space to study stars, and particularly the stars, the parts that we don't see from the Earth, is very much an idea of Meghnad Saha, and it originated in India. So ultraviolet is one of the major parts of the spectrum that has wonderful information about the nature of stars and galaxies. And this is where the wavelength is shorter than the 400 nanometers that our eye can see. It goes all the way down to 10 nanometers. And this is completely obscured by the atmosphere, so it doesn't require, so it requires a telescope in space. And initially, the ones that were the such ultraviolet telescopes that were launched by NASA initially were the Hubble Space Telescope, for example, and after that, telescopes like Galax, which were all ultraviolet-ready telescopes. It had cameras that had ultraviolet sensitivity, and it opened up a lot of amazing vistas of the universe for us, which we couldn't see using normal telescopes on the Earth. Here's an example of how the Andromeda Galaxy, which is one of our nearest galaxies, the picture was taken by Galax, which is NASA's mission, where you can see that you see the same galaxy, but what you see in the ultraviolet picture on the left are the young stars, stars that have just been born. They are 10 to 20, 30,000 degrees hot. And you can see that these stars are formed, are born only in the spiral arms, in the arms of the galaxy, not everywhere. They're not distributed everywhere. This gives us a key to understanding how stars are born and how stars first form in galaxies. And by studying these ultra hot stars, we can also figure out how many of these stars are going to explode to form supernovae, what will be left behind from these stellar deaths. And you can study the whole evolution of stars from these. This provides very crucial information for for a very key thing, and that's, for example, you can ask, how did our sun actually, how was it born? And it would have been formed in near one of these, in from molecular clouds near one of these spiral arms, and these kinds of observation gives us a very good idea. And that's where Astrosat comes in. ISRO's spectacular multi-wavelength space observatory, which was conceived in the 1990s, soon after Hubble Space Telescope went up. I was very fortunate to have been involved with Astrosat from the very beginning of its conception. It was finally launched in 2015, but over a decade, Indian astronomers worked with ISRO to develop this platform, which was unique in many ways. First of all, it has 5 telescopes. All of these observe in parts of the electromagnetic spectrum that you cannot see from the Earth. And as you can see, this has, of the 5 telescopes, there is a very interesting ultraviolet imaging telescope. I said Meghnad Shah's whole idea was that ultraviolet telescope should be sent above the Earth's atmosphere, from which we can study galaxies and stars. It has the ultraviolet imaging telescope, VVIT, but also has X-ray telescope, which I will talk about a little later. 2 different X-ray telescopes, the LAX-PC and the soft X-ray telescope. It also has the CZTI, which is a very unique kind of instrument that also observes in the X-rays to find out the presence of very active black holes in the middle of galaxies. And so the interesting thing is that they all work together. And so you have 5 telescopes working, observing the same object at the same time. And so, for example, if an object changes due to anything at one of the wavelengths and doesn't change at the other wavelengths, you will be able to observe them. So other than Astrosat, anybody else wants to do something like this, they will have to first get time on 5 different telescopes in space and then work them together. And here, the platform actually does that for you. If you get time to work on Astrosat, you will find that you're observing in all the different kinds of parts of the wavelength the same object. And that gives Astrosat a very unique facility. It was launched in 2015. It follows a circular orbit, 650 kilometers above the Earth, and it has in its payloads capacities to go from optical UV to all the way to hard X-rays in various things, 5 science payloads. And we have almost and now I think by about 12 to 1500 observations carried out, and of this, because we had some collaboration from Canada and the UK, some time is given to the international community. A lot of the international community can apply for time on Astrosat, and they do. But the 65% of time goes to Indian astronomers, and often we collaborate with astronomers from all over the world and use this amazing telescope. More than 1,000 papers have been written of the observations since 2015 on this from this amazing telescope. And the instruments were built in different parts of the country. TIFR, Mumbai, and Ayuka in Pune, where I was, together built some of the instruments. Some of the instruments were built by ISRO's own institutions in Ahmedabad and in Trivandrum and in Bangalore, and they were all brought together to create this very unique instrument where we can detect high energy particles and go right across the electromagnetic spectrum. And some of the spectacular results that have come are to do with the high redshift universe, the universe that is very far away, very young. And one of the big questions that we want to answer is that as the universe started, it was after the Big Bang, it was all very uniform, and you couldn't see, there was not much structure in the universe. And now we see a lot of structure. We see galaxies, we see stars, we see ourselves. At what point from the very dark universe where there was not much structure, um, uh, did we did all these stars form? And so the stars lit up and the universe was full of light. Before that, there were lots of particles, but they were not giving off light, right? So um, this phase of the universe, which was dark because there were no stars, at what time we believe it would be in the first maybe 100 million years of the universe, but we don't know. So we have to really look very far away. And in order to do that, you have to look at very high redshift. And so Astrosat has been giving us very interesting information about that. And if you look at, we're looking at how are there sources that generate photons because they are the earliest stars or galaxies that would have been formed. And as I've told you before, young stars, young galaxies actually have a lot of ultraviolet, extreme ultraviolet radiation. So Astrosat has helped us find sources of ultraviolet photons, 600 angstrom photons, which we which we wouldn't actually see with our own eyes. And this is because these things would be highly redshifted. And also, these at this wavelength, our eyes are not sensitive, but also they won't come through the Earth's atmosphere. So even if we had detectors, we wouldn't detect them. So as you can see, previous observations did not have any such detections, but this is we have detections right starting from a redshift of about 1.5 to higher and higher redshifts, where we have detected young galaxies using Astrosat. And this comes from collaboration with Kanak Saha leading at IUCAA. I'm just showing you one example of one of my colleagues who did this amazing work in finding, using Astrosat's UV satellite, the youngest galaxies and what they look like. And that is because it is made possible by the fact that the UV telescope, the ultraviolet telescope on Astrosat, has amazing capabilities. You can see here a comparison of the same field, image taken in the same field at the same kind of ultraviolet wavelengths from the best telescope before Astrosat, and that is on the right, called GALEX from NASA. And look at the left image, which is Astrosat's own deep field created by Astrosat's UV, NUV filter image. And you can see the difference. Can you see the difference? Just look at how much more resolution India's Astrosat has. Look at how much of how deep objects you can see on the right. They're all blurred. You can't make out whether they're stars or galaxies. And here you can actually see individual objects. The resolution is exquisite. And because it is very, very deep, you can figure out, you can look at the pink one circle on the right, and you will see just a blob. On the left, you can see individual galaxies, and you can study each of them separately. And so that is the magic of the ultraviolet capability of Astrosat. It is not a big telescope, but the instruments were so good that it has given us amazing information. It's one of the biggest success stories of Indian astronomy, and particularly Indian science from space. And if you go to the Astrosat website, ISRO website, you will find amazing pictures of the deepest images taken by the ultraviolet telescope on Astrosat. There are many others that one can do, other things one can do. One can take pictures of, one can take spectra of stars and galaxies. using UV instrumentation. And this is something we have to do in future missions. And this has inspired us to think about how to do UV astronomy to study the galaxies and black holes, active galaxies and faraway objects using future facilities. I'm going to talk about how to look at the ultraviolet pictures of the sun, which is what you see on the left in the next coming slides. In the infrared and near infrared also, there are ground-based telescopes on tops of mountains, but and that is because you can see that the atmosphere has transmission, which is very patchy, and in certain ranges of wavelengths, you can see light coming in, and so you can study them from the Earth, but you really have to go above the atmosphere into space to do good infrared observations, and we do not have an Indian mission yet that can do something like this. So JWST is the best, as I said, till now. X-rays is another part of the electromagnetic spectrum that is stopped by the Earth's atmosphere, and it has got a lot of information about the high energy activity that happens in galaxies. It normally observes things that are almost 10 to the power 7 degrees, 10 million degrees, 1 crore degrees hot. And so that is not the kind of thing that you would see with your eyes. I mean, there are many things in the universe that can get so hot. For example, if a star explodes and you have a supernova, it can produce gas that's hot. You can have around neutron stars or black holes, there are very strong magnetic fields and particles moving at relativistic speeds, close to the speed of light in these magnetic fields can become very hot. And when there's matter that's falling into deep gravitational wells in black holes, as they're falling in, the gravitational energy that is transferred to them can make them very, very hot. And so these things can be observed. X-rays, you can see a good example of X-rays. On the right, this is from a German satellite called Rosat. On the left, you can see an optical picture of some galaxies. You will know that there are clusters of galaxies there. On the right, you can see an X-ray image, a soft X-ray image of the same part, and you can see the gas that is 10 to the power 7 degrees hot, which is in yellow and red. Around the same galaxies, this is in the space in between the galaxies. This shows up in X-rays. You wouldn't see that in the optical picture that you take with a normal telescope on Earth. Also, the NASA's Chandra satellite has actually showed us how amazingly, this is a picture of the Crab pulsar, how neutron stars have a very hot gas plasma swirling around them. These are things you would not see in the optical. Now, the thing is, the specialist thing is, if you want to have an image that is made out of from X-ray observations, it is very, very difficult because, X-rays go through materials. So if X-rays go through materials, then you cannot build X-ray mirrors which will reflect light, normal reflection, and form an image. And so in order to image X-rays, the idea is that, because if you look at how normal light is reflected off a surface, it is like reflecting a football off a grid like this, because the spacing in the grid is much less than the size of the football. For X-rays, the size of the wavelength is the same same size as the spacing between atoms and molecules on a surface. And that is why the X-rays go right through. So somebody figured out that the way to reflect X-rays is to turn the grid around, and so that the average spacing between the molecules that you see is going to be smaller than the thing that you're trying to reflect. And that is why X-rays are have to be detected at grazing incidents, not normal incidents. They cannot come perpendicular to the surface, and that makes mirror construction very different. And so you can see what happens is that this is a Chandra observatory, NASA, which I was involved when it was being built. And you can see that it's got 4 concentric mirrors, and when the X-rays come, they are never more than 3 degrees from the surface, and so they get slowly reflected and it's about 4 meters long to the instruments, and so this construction is very different. So if you can see, NASA's Chandra had this stack of 4 concentric mirrors. Astrosat's soft X-ray telescope on the right, you can see, had the same thing, but it had a stack of 45 mirrors, which were all sensitive to X-rays, and that is the SXT that you can see in the Astrosat, and it has produced some amazing X-ray images, and it still continues to produce amazing X-ray images of objects up in the sky, and it has enabled us to study not just clusters of galaxies, but also black holes and stuff. And I'll show you one of my own images from Chandra, which illustrates what can be done. I use X-ray telescopes all over the world, and this is from NASA's Chandra. And if you can see that this is a picture of an optical picture of a galaxy, Centaurus A, which you can see what you can see here are normal stars like our sun, which are a few thousand degrees hot. But if you want to know where the black holes are and the neutron stars are, because the gas around them will be 1 million to 10 million degrees hot, then you need to turn on X-ray telescope, and this is what the Chandra deep image of the same galaxy gives you. And in this picture, everything is 10 million degrees hot. Everything here is a few thousand degrees hot.
Half an hour over.
You look at, yes, thank you. I'm almost winding down. Thank you. And so this shows in this picture almost everything you see is either a black hole or a neutron star, and these are black holes or neutron stars accreting mass from their companions, making them very, very hot. It also shows at the center of this galaxy there is a very big supermassive black hole sitting there, which actually has ejected a jet. So Astrosat has, as I said, the same X-ray capacity, not as good resolution, but it has also given amazing ideas. So the next astronomical instrument that was sent up by ISRO, with which my institution, IUCAA, played a very important role, was Aditya L1. It was launched only a little more than a year ago on the PSLV C57. It's got, and what it does, it actually goes to a place called the first Lagrangian point between the Earth and the Sun, about 150 million kilometers, 1.5 million kilometers away. 150 million kilometers is the distance to the Sun. That's 1% of the distance to the Sun, and it has got 2 major instruments and some others. The 2 major instruments, one of them is an ultraviolet camera that looks at the sun. I showed you how the sun looks very dramatic in the ultraviolet. And the other is a spectrograph that looks at the corona. This amazing orbit it has, there are 5 Lagrangian points between the Earth and the Sun, where if you place an object, it actually has either a stable or an unstable equilibrium position, because the forces due to the Earth and the Sun and the centrifugal forces all cancel out. The L1 is between the Earth and the Sun, and that is where Aditya L1 has reached and is now started amazingly to observe, and it is producing wonderful images, ultraviolet images. The instrument that we built at IUCAA was called SUIT, and it has got an ultraviolet camera, which is very, very different from the ultraviolet camera that you saw on Astrosat. And it has produced very wonderful images of the sun, of the activity that's going on the surface of the sun. I'm showing you the very first pictures that came out of SUIT. There have been lots of other pictures that are being published in papers right now that are helping us understand what happens on the surface of the sun, because these explosions that happen on the sun of very, very relativistic charged plasma. They reach the Earth and affect our atmosphere quite a bit. Another fantastic instrument that was launched towards the end of 2023 after Aditya L1 was XPOSat, which was almost exclusively built at the Raman Institute in Bangalore. And what it does is in hard X-rays, it studies the polarization of X-ray sources. So it studies about 30 to 40 X-ray sources that are very, very bright and studies their polarization. And the polarization is a different kind of information about the magnetic fields and the energetics of things like supermassive black holes, active galactic nuclei, and also very high energy emitting compact objects. I want to end by saying that the future of Indian space astronomy is very, very bright. And these are missions that are being considered by ISRO right now. As I said, this is not an official ISRO talk, so I cannot take any responsibility for whether ISRO is going to launch these in the end, but these are being discussed at various levels at ISRO as future missions, and all of these are very, very important worldwide missions. They're not just for India, but for astronomy in general. You have ExoWorlds, which is a very interesting mission that is being planned that will look for atmospheres around planets that are around other stars. As you know, since 1995, we have been finding planets that are in other solar systems, not around our sun. And we know about 7,000 to 8,000 such stars, such planets right now. But this is to study the atmospheres of these planets to figure out whether they have any molecules that can give us ideas of whether there is life on those planets or if there is any other very interesting phenomena that are going on these planets. So this would be an amazing mission. And my institution, IUCA, was also involved in this. There's something called Daksha, which is being built by IIT Mumbai, together with many institutions, including IUCA, where these will be 2 satellites that will be following up transients, which are sources that are detected by the gravitational wave experiments that are going on all over the world in LIGO, Virgo, and Kagra. Soon, India will have its own gravitational wave experiment in LIGO India, and these will be when a gravitational wave source is detected, these can be followed up with Daksha. There is an idea that India might have its mission to study the cosmic microwave background. And there is also the proposal to build a very large ultraviolet telescope called INSIST. I told you that we now do only ultraviolet imaging from Astrosat and from Aditya L1, but the INSIST will have spectroscopy as well as will be a much larger telescope to study ultraviolet missions. I'll stop there and I'll see if anybody has any questions. Thank you very much for listening to me.